Hi, my name is Alexa Van Hatten from Cornell University, and today I want to talk about how we can use a search-based technique, equality saturation, to vectorize code for digital signal processors. This is joint work with my collaborators at Cornell, Rachit Nigam and Adrian Sampson, as well as Facebook Reality Labs, Vincent T. Lee, and UT Austin, James Bornholt. To start with, I want to motivate our particular choice of target of digital signal processors, or DSPs, and I'm going to do that in comparison to a traditional general-purpose processor. So if we start with some program written in an imperative language like C++, we have this nice property where even if our compiler fails to find parallelism in this code, we can still get good instruction-level parallelism via dynamic techniques at the hardware level, such as out-of-order execution. However, DSPs prioritize energy efficiency, so they have simple in-order cores. This means that they expose a single instruction multiple data, or SIMD, instruction set that puts the burden of finding parallelism at the software level. So if we have the same program that's hard to vectorize, maybe because of a difficult to analyze for loop, and a compiler that fails to find auto-vectorization, we end up with sequential code that's slower and ultimately less energy efficient. Alternatively, the programmer can specify the ILP in their program via SIMD intrinsics at the source level. Here, loading to vectors at line 2 and 3, performing a vector add at line 5, and storing to back to memory in line 7. While this looks simple, this code can be an order of magnitude faster depending on your target. However, it's not always as simple to program as this particular example, and this can actually be a daunting task for programmers. The goal of this work is to then automate this process. So we start with programs specified as high-level scalar implementations that look like this, and we find efficient vectorization and data layout strategies with a particular focus on small, fixed-size linear algebra kernels that might require complex data movement in order to get full vector lane utilization. We embody these ideas in a compiler called Diospyros. So to give an example, here's a fixed-size matrix multiply of a 2x2 and 2x3 matrix. Our goal is to produce the output matrix on the right. Here's how we might optimize this code for a particular target, the Tensilica Fusion G3 DSP. We would start by loading data from memory into vectors, and then we would perform a target-specific shuffle. You can see how this works in the bottom right. So our shuffle takes in a vector of inputs as well as a vector of indices, and moves data around into an output vector based on those indices. And you'll see that the pattern of movement here matches the pattern of inputs you see in the output matrix. We would repeat this again, this time shuffling in order to enable a fuse, multiply, and accumulate, or vector MAC instruction. And then we can do the same thing for the final two elements in this output. So while this code is relatively complicated and requires all these different sort of manually selected shuffles, it's 4 times faster than the scalar implementation we saw previously run through the vendor's optimizing compiler at the highest optimization level. So our compiler Diospyros can find implementations like this automatically. Here's an overview of how it works. We start with scalar programs written in a DSL embedded in Racket, and then we use the Rosette engine, which provides synthesis and verification tooling to Racket in order to get programs in this abstract vector DSL. Our core technique that we use throughout this paper is equality saturation, which is an existing technique embodied in the egg eGraphsGrid library that lets you apply a series of rewrite rules in order to transform programs. Our particular contribution is applying rewrite rules to vectorization and finding rules that work well in this domain. We then have a traditional compiler backend that produces optimized vector C++ code for our particular target. I want to step through this diagram roughly in order, so we'll start with symbolic evaluation. So for symbolic evaluation, we start with an imperative program in our Racket-based specification language, here a matrix multiply. Rosette then lifts this reference specification to a symbolic output matrix. This is useful for our purposes because it allows us to apply rewrite rules without considering the imperative control flow and instead just focusing on the desired output. These reference implementations or specifications are parametric over size, so you can write them once and instantiate them for many different sizes. and they allow data-independent control flow. So you can have essentially arbitrary racket control flow as long as it doesn't depend on the specific values of the data. Here we have an example safe access for a 2D convolution that checks that writes are in bounds. Next, I want to touch on our core strategy, which is using rewrite rules and equality saturation. If you want to know more about this technique, I encourage you to check out the recent Popple paper from folks at University of Washington. The core insight in this paper is that we can see our scalar specification and our optimal vector program as equivalent. And further, we can understand this equivalence as a series of rewrite rules that transform the scalar specification into our desired vector program. So for example, we might want to show that this list of additions of inputs is equivalent to a vector add on vectors of inputs. So this is the same essentially as saying the equivalence shown at the bottom, that if we have additions on scalar elements of matrices, this is the same as first loading data into vectors, doing a vector add, and storing back out to our output. Here are rules that we use to actually accomplish this. So we start with a rule that says we can treat lists of inputs as concatenations of vectors, here of a fixed width of 2, for example. Next, we say that scalar operations can be converted to vector operations if they have the same instruction. So here, 2 scalar adds can be converted to a vector add. Then we say that vector operations can be fused. For example, vector add and vector multiply can be fused to a vector multiply accumulate. But in general, we might not know the order in which to apply these rules because multiple rules could apply at once and produce different final results. This is a core problem in the compiler's literature, and it's called the phase ordering problem, which is, in general, how do we know the order in which to apply our rules in order to reach an optimal program? We can see these two programs, the scalar specification and the optimal vector program, as existing in a large space of equivalent programs, where our entry into this space is achieved via symbolic evaluation on the reference program. Equality saturation allows us to essentially apply all of the rewrites to all potential programs at the same time. This might seem inefficient, but equality saturation is backed by a powerful data structure called egraphs that allows us to share program structure across these different candidate programs. Finally, once we've run equality saturation, we use extraction to pick the best program seen so far up to some cost model, and we use our backend to lower back to imperative C++ code with intrinsics. Here's a look at how egraphs work in a little bit more detail. So they start with a structure similar to a program abstract syntax tree, or AST, with a few differences. So the lines drawn in black are E-nodes, which are program nodes similar to AST nodes, and the lines drawn in red are E-classes, or equivalence classes. Here we don't have any equivalences on this program yet, so each node is in its own class. Once we apply a rule, for example, that list can be treated as concatenation of vectors, here it's just of width 2, so we don't have a concatenation. What happens is a node is added, but instead of duplicating the entire AST, it simply points to the children E-classes of the existing structure. So we're able to represent 2 entirely different programs, but share structure across the programs. If we then apply our rule that says additions on scalars can be converted to vector additions on vectors of scalars, it would look something like this. So we add the new node for vector add new subchildren for pointing to vectors, and then point those vectors to the existing nodes that represent the different children. And this is representing the idea that our original list of scalar adds is equivalent to a vector add on vectors of scalars. However, A, B, C, and D here could be even more complicated. For example, each of them could actually be an access to an array, A or B. So our list of additions of scalars can be converted to a vector add on vectors of individual array accesses. And that can then be used to show how we produce vectorized C++ code. So here, because we're accessing elements of A in one vector and elements of B in the other, we can implement those as loads from memory and then do our vector add instruction. If we have a slightly more complicated resulting DSL code, like if 1 and 0 are swapped in the order of access in B, we produce code that uses shuffle intrinsics. So here, because the elements of B are swapped, we produce a shuffle that passes in the indices necessary in order to still do the vector add computation. This brings us to the idea that equality saturation can apply all of these different rules, but then at some point, we saturate with respect to the rules. So this means that there are no more rules that you can apply to reach new programs. And as you see illustrated here, this doesn't necessarily mean you've seen all equivalent programs up to the language semantics, because the rules might not necessarily be complete. The next idea is that we use extraction to pull the desired program out of this search space, and we do this via a cost model. The goal of our cost model is to be really high level and not bake in as many specifics about the target architecture. The constraint it has is that it should be strictly monotonic. This just means that the cost of each program should be strictly greater than the cost of its subterms, which allows a more efficient search through the candidate programs. And our cost model is really captured by two ideas. The first is that vectors should be lower cost vector computations should be lower cost than an equivalent number of scalar computations. And the next is that we want vectors of memory accesses to be lower cost than other vectors. Our tool can actually mix scalar and vector computation, but this rule prioritizes vectors that can be implemented efficiently on the target architecture. Another challenge we ran into is the associativity and commutativity of operators. So if we had an addition over all of these elements, and we had rules that said that x and y could be swapped, and that the associative nesting level could be different, then we end up with a search size blowup across these different vector lanes. So we end up spending lots of time searching a small and similar part of the search space instead of getting to more interesting candidate programs. One solution would be to simply disable associativity and commutativity. However, in practice, we ran into issues where we'd have code like this, where a simple swapping of the order of operands into a plus would stop us from further vectorizing this code. So we took a different approach, which is to selectively apply limited associativity and commutativity in rules that we knew to be profitable. For example, we knew that a vector multiply accumulate rule could be really profitable, so we built a custom searcher. This is essentially the left-hand side of a rewrite rule that matches on existing programs in order to rewrite them. So this custom searcher had different flexible options per lane, where each lane could have different orders of associativity or be just the multiplication or a zero. This allowed us to search a larger space of programs and find more interesting candidates. Next, I want to touch on our evaluation, which will focus on the performance of the optimized vector C++ code. So here we have our speed up over scalar fixed size loop nest on the y-axis, shown with a log scale. And on the x-axis, we have different kernels of different fixed sizes. For example, 2D convolution, matrix multiply, quaternion product, and QR decomposition. The results you'll see here are from the vendor's cycle level simulator and are after 3 minutes of equality saturation. Compilation itself could take longer, but we timed out equality saturation after 3 minutes. Our performance is shown here with our tool in magenta. You see that we achieve good performance, reaching on average 3 times the performance of the best performing alternative. And that includes, in this case, library code that was, in some cases, hand-tuned to do well on this particular target. So that library code is shown in gray. The cases where the library beats us tend to be cases like the 16 by 16 and 4 by 4 2D convolution, where the fixed sizes of the data aligns nicely with the vector width. Next, we have an ablation study that demonstrates that our search is tunable. And what this means is that as equality saturation runs for longer, we explore a larger space of programs. And you see here that we have a plot that shows now the simulation cycles on the x-axis and timeout increasing as you go down on the y-axis. This is for a 10 by 10 matrix multiply. So you see that you can see that after 10 or 30 seconds, we achieve performance worse than the library code shown in gray, but after 60 seconds, we achieve performance better than the library code. This is really cool because a lot of synthesis and search-based techniques don't always allow you to terminate early and have successful results, but here we can set our threshold for the timeout and achieve code that is still equivalent even if it's not as fast. Finally, we have an application case study where we looked at the Theia computer vision library that has algorithms for structure from motion. This particular library call, decompose projection matrix, spent about 61% of its runtime on a call to QR decomposition, which was one of our benchmarks. So our benchmark implementation was about 140 lines of our imperative reference code, but it had over 65,000 floating point multiplies in the resulting symbolic matrix, which shows that even relatively simple implementations can capture complex computational patterns. In total, it took about 5 minutes to compile this function, of which 3 minutes were spent in equality saturation. And the resulting code is 2.1 times faster for the entire call to decompose projection matrix. So even though the source code did not spend as much of its time in QR decomposition and just spent a large proportion of the runtime, we still achieved an end-to-end speedup for this library call. So as an overview, our tool takes scalar programs and produces optimized vector C++ code by applying rewrites with equality saturation. And I want to leave you with this key idea, that we can use search-based rewriting with equality saturation in order to vectorize DSP code, especially for hard-to-vectorize small fixed-size kernels. Our artifact has been evaluated, and all of our code and experiments are open source, and you can check them out at the URL based here. Thank you so much for your time.